In my previous tutorial, I demonstrated how to write ARM assembly to perform direct-to-register programming on a Raspberry Pi. By directly controlling the GPIO registers on the ARM processor, we were able to get an LED to blink on and off. The problem, however, was that we wrote that tutorial all in assembly. The problem with programming in assembly is that assembly isn't a very scalable language, and as you add more features to your code, the code gets hard to manage, hard to understand, and is often not maintainable by other programmers unfamiliar with your code base. The correct way to do this instead is to use a compiled language. So in this video, I'll be showing you guys how to make a project and write code in C that will perform the same direct register functionality, all without the hassle of writing it in assembly. Also, to be alerted when I put up videos on the Raspberry Pi, Baremetal programming, and other low-level topics, hit that subscribe button and hit the notification bell. Now, the way we'll do this will be pretty similar to the first video. At the risk of being hypocritical, there actually is a little bit of assembly that we have to use. This assembly will be called start.s, and that'll be the glue code that gets the code control from assembly into our C code. Once we've compiled and assembled our assembly, we will then begin writing our code in C. Now here what we're going to do is compile our C code into an object file. What we have to do after that is take all of our object files we've created, so main.o and start.o, and use a linker script to assemble them in the correct order and produce our kernel 7 elf that the Raspberry Pi will boot. Now, what a linker script does is it actually pretty cleanly just lays out the layout of an elf image that you create at compile time. And you can actually put what order the symbols appear in and what segments and sections appear in what order. The reason we want to do this is we want the start symbol, so at the beginning of our code, our start.s here, to appear first in the image so that when the assembler creates the assembly and the compiler creates the elf, we don't accidentally have main.c appearing first without the startup code happening. Doing this in the linker script allows us to confirm that our elf is assembled in the correct order. And another thing we'll introduce in this video is the idea of a board support package header file. So in this case, we have the BCM2837 header file. Looks like written by Apple. I found this online. But basically, if you remember from our previous video, we were going through and we were pulling out all of these addresses from the datasheet manually and putting them into our code by hand. As you begin to interface with more peripherals on the chip, this gets very hard to maintain and honestly annoying to do. So people that produce chips often publish header files that have all of these addresses extracted and they define names for them. So instead of us having to manually define constants that we'll use, we can just use the value specified in this header file. So for example, for the function select 0, we can just use this word as opposed to this address. For the GP set 0, we can just use this constant instead of this address, etc. So currently we're in a spot where we have this assembly written. I'll kind of just walk through what this does. Line 1, we're saying section.text.boot. The reason why we have a .text.boot section is we want to specify in our linker file that this part of the code starts first, right? So we have this part happening in front of the .text. So when the ARM processor gets to execution, it goes to run start code first. And then after that, all we do is we have our start symbol, which loads the address of main, our actual C code address, into register 3, and then we jump to that address. This should never return. We should never get back to this point. But when main does return, if it ever does, we'll eventually get to the halt symbol, which just branches to itself and kind of infinitely loops. So yeah, now we can actually go into the C part of the code and begin to write code that will get ran on the processor, not in assembly. So now that we're actually executing code in main, we want to write two functions that will make our life a little easier when doing direct register programming. The first function is going to be a write32 function. That's going to take a address as input and write a value there. We'll be able to use this function and plug in these addresses from the header file, write data to those addresses. So the write32 function will take a void star of dest and a uint value. We need to do a type def unsigned int as uint, just so it doesn't yell at us when we compile. And what this function will do is it will cast the destination pointer into a destination U pointer, and we're going to write the value to that pointer. This is our write functionality, and this will return nothing. And then we're going to do the same thing, but we're going to have a read instead. So read32 is going to have a source, and it's going to only take in that source. We could do source view equals source, and then we're just going to return source, delete all this, and make sure it returns a uint. Cool, so now we have two basic functions that we can write and read to these peripheral addresses. Very cool. So now that we have those written, we need to do a few more things. All right, so in our previous video, we needed to set the function of pin 21 to be an output, right? So we had to write to GPF select 2. These are actually not spelled out in the datasheet in the header file, but we can add those in pretty quickly. So the offsets are going to be +4 and +8 for GPIO function select 1 and for 2. So we're going to take this here, and then we are going to take a register, a uint, and it's going to be the GPF cell 2, and we're going to say that it's equal to read 32 this address. This will read from this address to the chip and give us the current value in that register. Then what we need to do is we need to make sure that pin 21 is set to be a output, just like our previous video, right? So we're going to say that that value or equals 1 left shifted by 3, which is going to turn pin 21 into an output. Just the same as before, right? But then now that we have done this in RAM, right, this is currently on the chip in RAM, we need to actually put it back into this address here from the data sheet. So just like before, we'll do a write 32. We're going to write to this address this value. And after that gets ran, we have turned pin 21 into an output. Pretty straightforward. Now we're going to do like we did before in our previous video. We're going to have an infinite loop where we are going to set the output to be turned on, right? So we need to turn on pin 21 and turn off pin 21. And in between there, we need to have sleeps, right? So delay and delay. So the way we do that is just like we did before. We need to write 32 to the GPIO set functionality from the header sheet, from the data sheet, right? So the set. And what are we going to write there? We are going to write 1 left shifted by 21. And then we are going to do the same thing, but instead of the GPIO set, we're going to have the GPIO clear, just like before. So this is turning on pin 21. This is turning off pin 21. And then here, we're going to do a very lazy loop just to make sure that the chip actually sleeps for a certain number of cycles so we can actually see an observable delay. So what will happen here is we will do I equals 0, while I is less than, we'll do OX 80,000. We'll do 800,000 just to be safe. If we don't make that number high enough, what will actually happen is the LED will blink so fast that the human eye can't observe it, and as a result, it'll appear like our code isn't working, it's just permanently on, but that's not going to be the case, right? So we'll do that, and we'll say I++. And then we'll do the same thing. We'll copy this code, we'll put it down here. Great, we'll zoom out a little bit, just to kind of talk about it. So what have we done, right? We've created two functions, a write 32 to write to a location and a read 32 to read from a location and return it. We use that read 32 to pull out the current state of the GPIO function selector for bus 2 and save it in a variable. We're then adding some information, right? We're using the OR flag here, the OR operation, to add information. So we're turning pin 21 into an output, and this bit selector here is, comes out of the data sheet, just like our previous tutorial. And then we're taking that value and writing it back into this function selector here. And then we are creating a counter for our infinite loop, where within the infinite loop, we write to the GPIO set for pin 21, and we'll turn that pin on, and that's where our LED is going to live. And then from there, we take another counter and we iterate over it to create a delay. So nothing should happen here. It should just hang for some number of actual human observable time. And then we do the same thing where we write 32 to GPIO clear, and we do that to set pin 21 to be off and then sleep. And then this should run infinitely. So we'll pull up our terminal here. I never actually included the header file. Make sure you actually include your header files, otherwise it'll be very upset. 2837.h. Try this again. One thing we forgot to do is this needs to be a source U, not the source. If you try to dereference a void pointer, the compiler will get mad. So after we figured that out, we'll type make, and now the kernel 7 elf is created, and we can put the kernel 7 image onto our SD card and put it into our Raspberry Pi and see what happens. Let's do that right now. Boom, and there you go. You can see here that the LED is blinking on and off. Our delay timer is a little long. It's closer to like 5 or 6 seconds than it is 1 second, but that's okay. Anyway, guys, I hope you learned something in this video. Getting your code to be the same functionality in C as it is in assembly is not that hard. So if you'd like this video, do me a favor, hit like, hit subscribe, and I'll see you guys next time. Take care.